history somebody has or where they've been before. And based on that information, I can flash the right product at the right time that I think the person's likely to buy. My hit rate might be a little bit lower. It may not be 100% hit rate, but I can use that to try to drive more online sales. So because I have more data about a person, I can personalize an offering and content to them. Where executives today are trying to squeeze more value out of their data. The challenge is most executive teams stop at, I'm going to use AI to improve my business. And they never really get into the weeds. And this is something I've been saying for a while is, at the end of the day, our job is to understand how to get in the weeds and actually drive that value forward. And it's a really challenging problem. So I want to kind of then transition into like, what is the actual role of a data scientist? And I partition into 3 buckets. I have my funny little XKCD comic over there on the right, which is talking about, what is machine learning? It's dumping everything in and kind of stirring the pot. And if you don't like it, stir some more and maybe it'll figure it out. But anybody who's been in the industry knows that's not really accurate. That is a very, using the algorithms. The 3 core things that any good data scientist is able to do is they're a critical thinker, a statistician, and a software developer. Depending on where you are or what company you work for, the percentages may vary on kind of what you do or how you do it. But those are kind of the 3 critical foundations I see for anybody who wants to be a good data scientist that actually applies business value. So these 3 things pair to become a data scientist. And it's usually at about this point that somebody will say, well, I thought data scientists worked in deep learning, or I thought data scientists used PyTorch and TensorFlow. And that's one of the key things I really want to make sure that we call out up front when we're talking about like the business of AI and the business of data science. Machine learning is a buzzword right now. A lot of people are buying it, but it is still just a tool. Which is why I often use the phrase, if it sounds stupid, it is. And so, machine learning is a fantastic tool for certain situations, but we're going to walk through a few in just a second where it's not necessarily the best tool, or there may be other things that you might want to try or might want to use to solve a particular problem. And so I want to decouple data scientist from user of machine learning, because I think that is a piece of the job, but not necessarily every part of the job. Your role is not necessarily to build models. Your role and your goal is to solve problems for the business. And I find, especially once you get to a more senior level as well, the more advanced and more senior, a lot of data scientists have PhDs. It's really fun to do research, and it's really interesting to make breakthroughs. But there are very few businesses that can afford to support research and breakthroughs and that level of innovation. Most businesses just want something good enough to solve their problem. So let's really quickly go through an example of like how you would set up and approach a problem. My management team might go to me and say, hey, Keith, I need you to figure out how we grow sales. And I could say, okay, what data do we have? Maybe I can use this data to do X or Y. And the reality is I could take this statement, which is fairly ambiguous, and I can set it up as a wide variety of problems. So I could say, okay, well, I have our CRM or our customer resource management system, think Salesforce. I could turn that into a classification problem to see, of the people that we have, who's bought, who hasn't bought. Maybe I can even use NLP to read through all of our emails that are in there. And, at the end of the day, predict who's more likely to buy versus not likely to buy. Okay, so maybe I set it up as a classification problem. Or the other thing I could do is I could look for patterns across our existing customer base, and I could try to find things that emerge for our core customers or things that are common. Maybe we can change how we advertise, or we can change our targeting strategy. The next thing I could do is I could maybe turn it into a regression problem and look at the lifetime value of existing customers and say, well, maybe we just spend all that money in-house and just try to grow our existing customer base. And then the last thing is maybe I could say, we're running a bunch of campaigns and we're doing a bunch of things right now. Maybe I could just come up with, some sort of fancy optimizer that will identify the best way to net return and minimize costs. So increase that overall level of profit. But what I'm getting at here is, as a data scientist, when I'm given something which is generally going to be fairly ambiguous, like I have the objective of growing sales, I can set that up in a lot of different ways. So classification, clustering, regression, linear programming. I'm only listing 4, but there are hundreds to thousands of ways to skin the cat when we're playing this game. Or similar business value. The next thing that you want to think about when you're building a problem. So the only reason I bring this up is when you understand the problem you're solving, you want to make sure with management you're crystal clear on exactly the approaches you can try, and we'll talk about this here in a second. But also, what the real objective is and where the highest return on investment may be. And that's something, you can definitely make that decision. And if you have the data to back up that decision, absolutely do it. But at a lot of organizations, if you were to ask me, how do I grow sales and which of these 4 approaches do I want to take? I'm not sure. There's a lot of different options I have. And so what I need to do is just sit down in a line and make sure everybody's crystal clear on what we're going to do and what we're not going to do. The next thing that you want to think about is how your work is going to be delivered. So there's 2 ways almost every single machine learning project or data science or analytics project is delivered. Way number 1 is as a report. These are the best ways. These are the POCs. This is why 90% of things don't make it to production, because not all the time does it need to go to production. A lot of times the problem may be, how could we increase sales? I could build a few models and I could say, hey, turns out if we target these people, we'll grow sales by 3%. And that doesn't need to be a production system. That can just be a report that says, focus on this particular demographic and sales will grow. And I can get that to management and that project is complete. And that's a perfectly acceptable way to run a business. But knowing that up front as a data scientist is really valuable, because that means I can use whatever tools I want. I'm definitely curious to hear, who's a Python user versus an R user versus a SAS user or SPSS on the call. But the tools if I'm building something that's going into production, and that's not going to be rebuilt by a series of software engineers, how I approach that problem, it needs to factor that in. So I probably want to use something like Python that's extensible and can be picked up by software developers down the road. I see there's a question. I'll get to it in just a second. So I don't want you guys to think I'm ignoring you. So the second way that things are delivered is production systems, and production systems are going to be, this is where you hear about terms like ML ops. How do you take a set of data, build a model on it, deploy that model, score that model, and consistently score that model, understand when that model is getting stale or when the data's changed, retrain the model, redeploy the model, all in an automated fashion. Production systems are really challenging right now with regards to getting machine learning running end to end. Most organizations are not mature enough to have a lot of machine learning has been pretty popular for 2 to 3 years. I'm still pretty confident in that statement because there's a lot more that has to be factored in. When you're dealing with a production machine learning system or a production analytics system, you have to spend a lot more time on Q&A and making sure that it is extremely robust. So knowing that up front is really valuable, and it may be as easy as asking your manager or your supervisor, hey, will this be deployed or am I producing a report? Because it's going to save you a lot of headache down the road. So some general tips and tricks. To ensure success up front when you're dealing with the data science problem, you probably won't. Sounds negative, is negative. Machine learning is not a magic bullet. I think anybody who deals with it a little bit knows that. However, it projects out of the gate. So instead of guaranteeing success, let's account for the unknowns and let's figure out how we can address those really easily. So decide on what the objective is. Select clear, measurable objectives. One of the examples I like to use here is when you're talking to management, say, you know, I can get a model that is this measure of accuracy. And to them, accuracy means something very different than what it means to a data scientist or to somebody who actually lives in the space. To them, accuracy is some term that they've kind of lived their whole life understanding in the English language. It doesn't necessarily mean number of correct answers divided by number of total answers. So you want to be really crisp about even deciding what the metrics are going to be that you're using to judge the work you're doing. So in a traditional classification problem, say, you know, we think an F1 score of X or a precision recall score on a minority class of X is acceptable. Particularly when you start to get into really complex problems that have to be broken down. You know, if the world was as easy as Kaggle made it out to be, we would all be in a good place and everybody would be extremely gainfully employed and there would be millions of models running everywhere. The challenge is it's not. Most problems you're going to be asked to solve as a data scientist are really complex and you're going to have to learn how to break them down in different ways. Subject matter experts can kind of help you do that. The next thing, identify approaches to try up front. This is one of the things that I've kind of learned over my history is particularly when you're entering into a world with a lot of unknowns. If you're trying to solve, for example, we talked about a classification problem. If you're trying to solve a classification problem and you've set it up as such and agreed with your management that it's going to be a classification problem, make sure that they know, here are the things we're going to try. We're going to produce a report on kind of what works best, what I fall into this trap myself. It's really easy to get sucked in and say, ooh, if I try one more thing, I can maybe get a little bit more accuracy. If I try one more thing, I can maybe improve this score ever so slightly or reduce this variability. And, you know, sometimes you can afford that, but a lot of times not. So do what you say you're going to do and then report out. And then if you want to continue the work because there's something leading, you know, make that decision then. Don't keep trying. Because for a manager, one of the most frustrating things in the world is a 4-week project taking 8 weeks. The last thing, time box. Oh, not the last thing. Time box all efforts. You know, just kind of to my last point. And stop what you've achieved, what you have intended to achieve. It's really easy, particularly if you are, you know, I don't know how many of you guys are kind of PhD researchers. It's really easy to say, ooh, I think I could do this and I think I could do that and I'm going to write a paper about it. There is an audience for your paper. It is probably not your CEO. I know this is a really aggressive negative view on like the theoretical world of machine learning and data science, but it's also something I don't think a lot of people say openly. So I apologize if I'm being overly blunt about it. And then last things, before you get started on any problem, and then we'll get into some meat of some like real cool complex problems. Understand how a problem is solved today when you're actually approaching it. I have a general theory, which is I used to have a lot of customers come to me and say, hey, I'm going to use machine learning to you know, find oil. I'm like, well, can you find oil today? And they're like, yeah, but it takes a lot of drilling and a lot of trial and error, and we don't really have any data that leads us to it. Like, okay, well, it's probably not a good problem for machine learning then. It's not, you know, you can't just dump data in and expect to get immediate results out. And so the rule of thumb I use is when you're starting a project, if a person doing it full time wouldn't be able to look at that data and find answers, then it's probably not a good fit for machine learning. Know how to segment a problem appropriately. Understand the viable technologies that you want to test up front. This is part of really scoping things effectively. Understand your business's resiliency to non-determinism. This is a mouthful, but one of the biggest problems I've seen is, depending on the industry you're in, they are more or less susceptible to or willing to accept machine learning answers. So here's an example. In retail, if you build a model that tries to predict who's going to buy or not, they are perfectly comfortable with that model being absolute garbage. So which could be very bad, meaning that the actual metrics around the model could be poor. Whereas if you shift over to something in supply chain and you go to, and you're using machine learning for forecasting, for example, this is kind of one of the unanimous applications of machine learning in supply chain. They are not nearly as resilient to non-deterministic answers, meaning if I say that there are going to be a demand of 20, we'll say 20 computers at this store every day, and all of a sudden my model spits out 600, that model may be the most accurate model compared to anything that they've had, but that 600 spurious outlier that the model produced because there was some known, there was something in the data that made it predict 600 is not going to be accepted really well by management. And so understanding your ability to produce wrong results for the business is really important before you get started as well, because it's going to influence your technology choice. If I'm not willing, maybe I use something like an ARIMA instead. And then explainability and interpretability is important. If you're really accurate and you're 100% accurate all the time, it doesn't matter, but almost nobody is. And at the end of the day, you have management that's making a lot of different decisions. And so being able to explain to your management exactly why a model made a decision that may have been a wrong decision is really important. There's some cool technologies that help with this, and I'm happy to send more info on that to anybody who asks. Really quickly, there was a question of like, what department does a data science team live in? Are they centralized or distributed? Most organizations, most big organizations are generally going to have centralized data science teams. And it may be per group even, or per business unit, they have a centralized team, because that way they're able to share technologies and share innovation. There are some businesses that do have a decentralized organization out on the team with subject matter experts. This is honestly probably the more effective way of doing data science, but not a lot of organizations do it today, because it also, it's easier to hire data scientists if they're working in a collaborative, fun, innovative, startup-y environment. Another question about managing or setting set objectives to business leaders and stakeholders, or let's see, sorry, I'm just going to read it because it's long. How do you work with management to not promise too much? Yeah, it's a real problem with data scientists, in that almost every data scientist or somebody who is in this space is a really practical person. They're a critical thinker. They know that there is the complete possibility of failing. And so how do you navigate projects that are judged solely based on their accuracy, but you can't guarantee that up front? It's like the old sales methodology, which is like, you always want to bring on salespeople that say they're going to go sell a lot of business, but you're only going to hire the people that say they're going to sell a lot, and they may not deliver on a lot. And so how do you actually do that up front? And so one of the best things is making sure you have a management team bought on with analytics. Be right more than you're not right. And then the other thing, and this is why I brought up earlier, is understanding how the problem is solved today. If you have a problem that is extremely manual today, buying that speed up from a person doing it manually compared to machine learning or data science or analytics is extremely valuable. And it also gives you a little bit more confidence that it can be done in a model. And so those are kind of I know that's a low-hanging fruit, which is like selectively pick your problems to build some confidence on things you can do correctly. It doesn't always work, and I don't have a good answer for all of that. That's part of why you have an innovation budget at a lot of big organizations. It's getting dark out here. I realize I just didn't turn my light on. Maybe I'll do that in a few minutes. Yeah, just a real quick, just kind of housekeeping note. If you guys do have questions, you're sending them directly to me. Just post them in the chat, or feel free to unmute and ask. We're all friends here. Oh yeah, I definitely need to turn my light on.
Yeah, if you wanna just take a little bit and take it on. Definitely.
All right.
Yeah. And meanwhile, if you have any question, you can actually unmute yourself also. We want to make it a little bit interactive today. See if we can get your answers. Okay.
Yeah. All right.
Okay. Good.
Let's talk some things we face. I see some familiar faces on the line here. So super excited to talk about some of the stuff I've been doing, and I can circle up with you guys later. But I will definitely say, as somebody who worked in the pure play AI business and moved to supply chain, it's been a real challenge to translate a lot of the things I learned, particularly, most machine learning problems at companies today are set up as supervised, unsupervised, semi-supervised problems. That doesn't necessarily work in supply chain all the time for a variety of reasons. And we'll talk about that. So on to the first one, which is part of what we do with our autoscheduler.ai organization. So what we do is we at the end of the day, it's called orchestrating a warehouse. There are a lot of different things that have to happen at a warehouse. In particular, you have really big sites. So there's customers like Procter & Gamble that we work with. And at a site, they may have multiple buildings. So there's one building where a production plant is. There's another building for storage A. There's another building for storage B, another building for storage C. And they may have a few hundred trucks that are expected to come drop off goods and come and pick up goods to go ship to customers on any given day. And so there's all sorts of tasks inside of all of these warehouses and buildings that have to occur in order to make everything work. And what I've learned, particularly in supply chain, is this is very manual today. And this is a very, grit and elbow grease type of industry. And so if you think about some of the core things that have to happen, is you have dock scheduling, which is what truck shows up at what door at what time. You also have something like loading, which is when the truck is in the door, who is actually putting pallets or boxes on that truck. And you have unloading. So if a truck is in a door and it's full and it needs to actually go into the warehouse, how do you unload that inventory or those goods? And then if you're unloading that inventory and those goods, is it going into the warehouse or is it going onto another truck that's actually scheduled to go out? In some cases, and I could probably go for days and wax philosophically, but I won't. In some cases, some of the things that need to get shipped out aren't even on pallets yet. So they're sitting, either in bins or in inventory cases somewhere out in the warehouse. And so I have to go and I actually have to pick a pallet. So when I say pick a pallet, it is literally I have to go and pick all of the individual cases, put them onto pallets, wrap those pallets, put them onto trucks. And so this is another activity that takes more time, with all in the end goal of how do I actually make sure that every order that a customer needs gets to that customer in time? This is probably something that most people don't really think about, but supply chain is a really complex business. How did something from Amazon Prime get to me in 2 days? Well, a lot of math went into that. And so let's talk about just this warehouse orchestration problem. There's all these different activities. There's all this inventory we have to manage. This is an NP hard problem. We want to be able to create perfect schedules that tells us exactly what to do when, down to every person that is working at a facility. And when I say at a facility, I mean in all buildings across the facility. And so when I say scheduling is an NP hard problem, this is something, there may not be a good general solution. There may not even be a way to verify if something is the best solution. And so if you were to think of it mathematically, it's like a really complex, stochastic differential equation. So lots of, there's a lot of math. There's no guarantee you're right. And as a data scientist, I'm faced with this problem and I say, okay, well, what can I do to actually solve this challenge? How do I break this down to better understand how we can deliver this to customers? Because we had customers that were asking for exactly this, is we need some way to orchestrate all activities in a warehouse. And so the first thing that we did is we sat with them and we said, okay, here are some of the key priorities. So just like I talked about, we said, all right, we're going to break this into a series of problems and we're going to understand which problems are more important than the other problems. So, first thing, we want to make sure every shipment that is going to a customer gets out the door on time. There's all sorts of weird things that happen in supply chain. Like, for example, last week, Walmart announced that it is increasing its OTIF percentage to 97%. OTIF means on time in full. meaning that if I ship a truck to Walmart and it is either not on time or not full, they're going to charge back 3% to me. So I'm going to have to pay Walmart for the stuff I delivered to them because either it was missing something or it wasn't there on time. So getting things out on time is really important because you can lose a lot of money this way if you're not efficient. The next thing I want to do is, okay, make sure my customers are happy. Problem 2 is, can we minimize transfers between facilities? So can we minimize the amount of times we have to touch something? Because every time we touch something, it's cost. And then there's number 3 is, can we minimize touches inside of a facility? So instead of putting something on a shelf, taking something off a shelf, putting it in a truck, is there a way to just take it from a truck, move it to a truck? Or take it from production line, move it to a truck? And then number 4 is reduce time on shelf. How can we actually factor in inventory or age bands? So if I was dealing with a product that can only be on a shelf for a given period of time, I want to be able to factor that in. And then on top of it all, this needs to be a production system that's running in real time and actually creating dynamic schedules for these customers. So as a data scientist, I look at this and I'm like, oh shit, classification is not going to help. Sorry for the language, guys, but
I'm assuming that there is a time series component in all these problems, right? It should be, because if it's on demand inventory, then you need to predict what you need ahead and so on in time. So
you're spot on.
So I've been looking in. I work with a nonprofit, and I've been looking into models where I'm trying to fit in classical models with time series, and I'm struggling with it, and there's not much literature. So if you have anything, can you just...
Yeah, I can definitely tell you what we did. I know there's some folks on the line as well who could probably help there. I see Randy Groves on the line. I don't know if you want to get with him afterwards, but
I don't want to hijack this, but if...
No, you're good. Yeah, and I'll talk through kind of what we've done and how we approach the problem, but I do know Randy and his team have a ton of experience in that particular space. And so definitely connect after if what I say doesn't help.
I live in Leander, so probably your neighbors, maybe.
Cool. I'll see you at Casa Costa. So how we approach the problem, and I want to be respectful of everybody's time because I still have reinforcement learning and other cool stuff to talk about, is we said we wanted to, decide on priorities and heuristics and things we can do. So getting shipments out on time. The first thing that we had is we knew that we had this input that was a transportation schedule, which was what needs to go where, when. And so based on the transportation schedule, we need to be able to create some shipment plan that is realistic. The problem is the transportation schedule is not realistic because nobody cares. If you're a trucker or a trucking company, a carrier as they're called, they don't necessarily care about your internal operations. They'll just say, hey, we're showing up at 9 a.m. Make sure that whatever I need to carry is ready to go by then. The problem is if it's one carrier, it's not a problem, but every carrier says, hey, I'm going to show up at 9 a.m. Be sure it's ready to go by then. And I only have 5 guys that can load trucks. So that's where the problem gets a little bit more complex. We have to do some math, and I just put a generic math box, because we'll talk about technologies here in a second, to build a shipment plan that's feasible. But what other data do we have? So we have a warehouse management system, and we have an ERP system. So from those things, we can pull what inventory do we have in our yard? So maybe not necessarily in our warehouse or in any of our warehouses, but sitting in a trailer out in the parking lot. Yard is a cool name for parking lot. You have inventory inside of a warehouse. You have facility constraints. For example, how many doors do I have? How many people do I have? So the work capacity constraints. How many people do I have to perform different tasks? I also have a production schedule. So am I making anything? Is my inventory level going to be changing even though no shipments come in and out? And how can I account for that? So can I commit to promise some of these goods or treat it as a time series problem to actually better create the shipment plan in the future? And then on top of that, you have a few other constraints. So you have activities that have to occur in order to actually build this optimal shipment plan, or at least a feasible shipment plan. So I need to understand how long does it take to build a pallet? If I need to actually go and put all of these cases onto a pallet, how long is that going to take me? if I need to go and actually move things from the parking lot or the yard to a door, that doesn't happen instantaneously. I have to build a buffer of time in to actually do this. And then I have to load and unload. Trucks don't magically pull into a door. Everything gets pushed on and they drive off. You know, you have guys with forklifts moving things onto trucks. And so there's other constraints of like nothing happens instantaneously like it does a lot of times in the modeling world that have to be factored in. So some of the technologies now, I'm going to segment this into 3 parts. So the first part is, what are some of the things that we can learn and what are some of the things that need to be optimized? So looking just solely at this math function, you know, the data scientist in me says pretty clearly, okay, this is not a classification problem. This is not a regression problem. This isn't a time series, either of those supervised machine learning problems. What technologies would enable me to take in all of these different constraints and considerations to actually build a good model? And so, okay, there's a few options. Maybe I use convex optimization, maybe use some advanced heuristics. You know, convex optimization will probably be better, but it might be slow. So I need to check and see how fast it is. Advanced heuristics might be really good, but I have to customize them for every site, which is going to be a real pain in the butt. Maybe I can build a digital twin, and that term is completely overused these days. But something that is able to treat this as a time series problem and understand, okay, now if I were to play this forward, what actually happens? And then maybe use some optimization technique around that. Digital twin, or I'll call it a simulation environment, is probably a little bit more accurate. And then there's other technologies like reinforcement learning, really promising, really good for control system based stuff, but maybe not able to do this out of the gate, and it might take forever to train. That's like a 5-year project. Looking at some of these other things, you know, I can segment them out and say, well, you know, my facility constraints, my work capacity, my production schedule, all the timings that I have to actually pull, you know, this data is static and it's coming from a database, but that's not really true, right? How long it takes to move something is going to depend on the weather. It's going to depend on the conditions outside. It's going to depend on who's working. So maybe I can use heuristics or moving averages or machine learning to make these pieces of the solution and these inputs more intelligent for the optimization technology that we decide to use. And so kind of fast forwarding, so these are, as a data scientist, I have to figure all this out. For the sake of time, I'll kind of skip to the end, which is, in this case, we actually built a simulation tool that is able to say, for this point in a warehouse, run anything forward. And to answer the time series question that came up a second ago, how does this actually factor in? And how do you treat this as a time series problem? We can basically, in that simulation, say, for this shipment, we know how long it takes to load, because we have that information. We know how many pallets are on that shipment, and we know how long it will actually take to pick all of those pallets. And so we can almost, you know, we can say, starting now, if you started, how long would it take? Okay, given how long it would take, we can use some sort of convex optimization or optimization technology to understand when it needs to start, and based on inventory and all of the other orders that need to go out, when is the best time for that particular shipment to start, while factoring all of these other things in. So, you know, our simulator pretty much tells us how long things will take in silos, and our optimizer figures out how to put all those silos together into something that's actually feasible at the end of the day. So for some of these other things on how to actually set constraints, that's where machine learning comes into play. Sorry, I'm gonna click here. There we go. What we're doing right now is we're leveraging some heuristics to actually update these constraints in all of these times. But one of the next things that we're moving on to is using pretty simple classification or regression problems to actually update these per site, so we are consistently learning from how people are operating in real time. So kind of jumping to the finish of problem number 1, which is a data science supply chain problem, is, you know, this isn't a reinforcement learning problem. We didn't start there. We found something that worked, which happened to be, you know, a digital twin plus some heuristics plus convex optimization for actually producing optimal schedules. Machine learning was valuable to us and is valuable to us, but in supplemental fashion. It is not the core value that we are driving with the business. And that's, I think, where a lot of CEOs get tied up, is they think machine learning is the core value, but us solving this problem is the core value. And machine learning helps, but it is not even the core enabler. And then the last thing, and I was remiss not mentioning this earlier, you know, this is a AI and big data meetup. 90% of the work you do is all around data and integration. 10% of the work is modeling, if that much, in most problems. So any questions on that before I jump to problem number 2? And I'll kind of go through this one pretty quickly, just for the sake of time. Okay. I'm guessing no questions. If anybody else in this group works in supply chain and has different approaches to solving these problems, I'm all ears. I would love to chat. So the next problem is a little bit higher up in the supply chain. So we started low with the distribution center, which is, what box goes on what truck when. Now it's how many trucks do we need to order for a source destination pair? So this is a process in supply chain known as planning. And so what planners have to do is they have to go and call the trucking companies and say, hey, I'm going from Austin to Waco, and I need 4 trucks on, Thursday. All right, today's Thursday, so Saturday, for that particular route. And so they'll actually get that booked in, and they have to actually commit to that for all of their different lanes. And there's some systems that exist, like a transportation management system, that helps with that. But very infrequently do you find that planners who are committing to this transport well in advance, so generally they have to commit 24 to 48 hours in advance at a minimum, are factoring in what's happening 20, 30, 40 days in the future. And so what generally happens is, because they're not taking a long-term view on the future, is that you end up with a lot of variability. It'd be really nice in any business if you could say, I need 4 trucks every day on this particular route or lane, as it's called. But what we see is you need 4 one day, 2 the next day, 16 the next day. And that's really a function of your orders aren't all coming in at the exact same increments. Like sometimes you get more orders on Friday, and by the time that makes it all the way to the planning system, it's created a little bit of a whiplash to where your planning system isn't really quite sure how to react. And so your planners do the best that they can to try to smooth everything out, but you end up with a lot of variability. So again, we're talking about scheduling. This is an NP hard problem. It's combinatorial optimization. I won't go too much into the weeds here because we've already kind of covered it. But even before we're talking about how do we solve this problem and how do we actually say, we know how many orders we have and what our forecast looks like for the next 30 days, how do we take that and translate that into trucks to order on a given day as well as into the future? And that's really what we're trying to do here. So thinking through this as a data scientist again, we say, all right, we know we have some total demand on each lane. Again, you may have many lanes inside of your supply chain network. The example of a lane being like Austin to Waco, or Austin to Dallas, or Austin to Nashville. And how do you take this problem and actually create individual transportation plans for every single one of them? And so, if I were to think through this problem, I first need to understand some of the constraints. Okay, well, I can look at demand as a combination of orders plus forecasts, but I also want to factor in, like, what is my acceptable window to delivery? And the example I'll use here is Amazon Prime. That acceptable window to delivery is 2 days. Not everybody operates that way. If somebody puts in an order, maybe I can deliver it in 2 weeks. Minimum delivery time, it needs, it can't be here before 3 days. So I have, at a minimum, it needs to get there 3 days from now. And at a maximum, it needs to get there 2 weeks from now. So I can factor in that window as a constraint. Time is a variable in this particular sense. And so outside of that, I have some other things, right? I have constraints at each distribution center. We already talked about the fact that we have constraints on how many times people can case, or how people can case pick, what the lead time looks like, how long it takes to actually load a pallet, what the lane lead time might be. It takes a day to drive from Austin to Dallas because I-35 is terrible. We also have costs, which are other levers that we can maneuver. The cost of a carrier on a Tuesday might be $800, but a cost of that same carrier on a Friday might be $1,200 because you're playing the spot market, which is like a little small capital market for trucks that's geographically regionalized. And so I have to try and consider all of these things, again, when I am figuring out when I want to send trucks where. And so the first thing that I as a data scientist might do is say, okay, again, this is not a classification problem. This is not a regression problem. This is an optimization problem. Let's try to figure out what technologies exist that can help us there. But, we talked about total demand and knowing how many of every single item was going to be ordered and forecasted to be ordered. But, how do I translate that into trucks? Because that's really what the output is here. So the next thing you have to think about is, if I know that, if I'm able to build an optimizer that does all this, it can say, send these individual units. So let's say we're talking about cans of soup. You need to send 21,000 cans of soup from Austin to Dallas. Well, that doesn't really help me figure out how many trucks it is. So I know what order should go when with this optimizer, but I probably need a little bit more than that. And so you have to, you turn the problem into something that can be broken down a little bit further. Well, first you have to understand things are generally shipped in a case. So a case may be 6 cans of soup. Cases are combined into pallets. So there may be 24 cases on a pallet. There may be multiple pallets in an order. So customers are ordering, customer A orders 2,100 cans of soup. Customer B orders 5,000 cans of soup. How many pallets is that? And then those orders and pallets need to go on truckloads. Now, this isn't a perfect science here. You can have orders that are below the pallet level, et cetera, but I don't want to go too deeply into the lore of supply chain. I'm really talk a little bit more about the math of what we're doing. So at the end of the day, I have to be able to translate the units into truckloads is kind of what the core problem is. And so what I can do is I can say, all right, I have an optimizer that can tell me exactly how many units need to get sent. I then need to build a pallet builder that tells me of all those units, and they could be mixed units. It doesn't necessarily have to be the same size and shape and weight can of soup. How many of those actually fit on pallets? So I need to have something that builds a pallet. And then if I have something that builds pallets, I need to know how many pallets actually fit on trucks. And to do that, I need to understand what weight can a truck have. So if it's going to Alabama, it can have a certain legal weight, whereas if it's going to California, it needs to have a different legal weight because the United States is cool like that. And so I need to have a load builder that's able to factor all this in and figure out how many of these pallets will actually fit on a given truck. So I have broken this problem of let's take demand and convert it to trucks for every single lane into an optimizer, a pallet builder, and a load builder. And then the last piece is, if my optimizer is good, it will tell me exactly how many trucks I need and the process will go really smoothly. But in most cases, your optimizer is going to guess. You go through this process, you figure out how many loads you have, and then it says, I have 3.5 trucks. Well, you don't want to ship 3.5 trucks. You want to ship 3 trucks or 4 trucks. So this is going to be an iterative process. So some of the technologies is, if I'm building an optimizer, again, linear programming, mixed integer programming, I could try reinforcement learning here again, but this is core optimization. Pallet building, a little bit of an easier problem, a little bit more constrained, something that's fairly well known. You can treat this as, heuristically, you could probably do this. You could use a knapsack solver. You could use mixed integer programming. You could use reinforcement learning. You could maybe even use like a bin pack solver. I don't know if you guys are familiar with that term. And then with load builder, same story. So what we ended up doing here is, again, it was all about driving that value as quickly as possible and where it was important. So I talked about, particularly on the load builder, being able to factor in truck weight, dimensions, et cetera. The other thing that didn't get accounted for is speed. You need to be able to load these trucks stupid fast, for lack of a better term, because whatever your optimizer is may have to run 10,000 times if you have a really complex network that you're trying to solve. And this is something that needs to happen at a minimum every day. And, I don't have a supercomputer and I can't afford one. So I need to find some really fast, good way of approximating all of these steps and getting a solution that's feasible. So what we ended up doing was using linear programming. So I don't know if you guys are familiar with LP, but it's a traditional operations research technique for setting the constraints of the network and solving the network. We have a knapsack solver that's capable of actually building pallets and building good, accurate pallets. And then we use reinforcement learning for the load builder. Load building is one of those unique things where there are too many constraints, particularly when you're loading a truck, that need to be factored in to where a heuristic solver is feasible in the time needed. And so these are kind of the technology choices we made. Some of our learnings along the way and are using, if you guys do work with linear programming, using a tool like IBM's Cplex for solving is extremely valuable. Open source quite hasn't gotten there for actually solving LPs. The closed source offerings are still better, and we did a bunch of benchmarking. Using Cython in production systems is really valuable, particularly when we're talking about reinforcement learning. It's sped up our model significantly. You know, we're talking a factor of 10 to 20 when it was actually scoring on customer data. Using OpenAI for building gyms. I don't know if any of you guys have dabbled in reinforcement learning, but OpenAI is fantastic and enables you to try out a lot of different policies and see what works. OR tools, open source Google toolkit, has a lot of really good solvers that are fairly well optimized. Good knapsack solver, and that's particularly what we used. And then another product that we actually bought was weights and biases. If you're trying to collaborate across a team, we found weights and biases to be really good when you're training a series of models. You need everybody to kind of chime in and see the same thing. I consider it kind of a more advanced version of TensorBoard if you guys are familiar with TensorFlow. Here's a picture of it. So let me jump kind of to the end, which is one of the things I was really critical on machine learning out of the gate on where it adds value to the business and what you want to make sure. But you know, the thing that, especially in supply chain, my systems are not really resilient to models not being perfect out of the gate. And so machine learning is not a good fit for everything we do. Traditional optimization is, but machine learning can add a lot of value to some of the sub-problems and sub-domains that we approach. Now, a lot of you guys are probably using machine learning out of the gate. So I wanted to kind of let you know about some of the other open source technologies that I have found helpful when you are building models. So one of the first ones is pandas profiling. We'll teach you everything you need to know about a data set. Does take a while to run, but really valuable when you're trying to understand everything about a data set, and has a really cool like HTML reporter. And then also in the AutoML space, there's some really good open source technologies. They're not going to be the best that you can get out there. There's some really amazing closed source technologies available. But if you just need a good model and you don't have the time to spend, you know, setting up random forest or XGBoost with all the different grid search, you know, hyperparameter tuning, try something like a Teapot or an AutoKeras or an H2O, and they'll generally spit out a model that's pretty good and save you a lot of time. So getting hired, and I apologize for kind of blazing through this, and I see there's a question on here as well, so I'll get to it here in a second. But things to prepare for in an interview. Again, statistics, code quality, the process of machine learning. You know, I can train a monkey to go use a random forest if need be. Really, in any interview, they care a lot more about your thought process and your fundamental strengths on, you know, how you approach problems. And then having extremely high quality code is really valuable because you'll be doing a lot more than solely building models in that job. You'll generally get asked why you got into data science. Almost nobody started in data science. Everybody kind of had a circuitous route to get there. That's not going to be true in 10 years, but today it is. Technical questions, you know, always know how random forest works when you walk in an interview. It may not be something that you get asked, but you know, there's a high probability they either ask you about, you know, how does PCA work? How does random forest work? How does XGBoost work? One of the more commonly used models are support vector machines. And if you're a deep learning expert or you're going into a company with visualization focus, they'll ask about convolutions or recurrency. The last slide, and then I will be done, is you're probably going to get a data science challenge. So when you are faced with that data science challenge, it's probably going to be a classification problem. You can probably train for it on Kaggle. There are a lot of really good notebooks that people already put on Kaggle walking through problems. Understanding how people approach problems is important. So, this problem is probably going to have categorical variables. How do you handle that? It's going to have missing values. How do you impute missing values? The grader is going to want to understand how you actually split data, and if you build your model appropriately with trying to factor in, holdout set or a testing set. They'll care about the results you get, but at the end of the day, they're going to care a lot more about your code and process, and that's what you'll be judged on. So for the folks on here that aren't in machine learning today, I apologize for talking about a lot of really complex technical things fairly quickly. But some of the good tools I've seen to get started, and there's a lot of really good YouTube channels out at this point that have tutorials, but Weka and Orange are no code options. So if you're not quite comfortable with coding quite yet, you can try those out. Python is generally what I would recommend if you really want to be serious about machine learning, because it's the most, it has the best libraries. It is generally the most used. R is a really good statistical language. It's how I got started. MATLAB, if a lot of engineers learn math. We'll call that the advanced version of machine learning, because that's really when you're talking about more data engineering. So I just talked about a lot of things. There was one question on the line about way back when I was talking about warehouse orchestration and how we actually performed all of the scheduling about, so what I define as a digital twin, and really how that operates. And so just some general comment, like, why haven't other people done this in the warehousing space, and why aren't their competitors doing it? And the reality is there's a lot of really complex optimization, and because this is an NP-hard problem, there's no really one right answer. And so it's how do you want to approach the problem? And in this case, I'm referring to a digital twin as, can I heuristically and in some simulation environment walk through a day in the life of and all of the activities that will occur? And then based on those things, use an optimizer to kind of switch activities or create activities that will drive further value. And how do we prioritize that is kind of some of the work that we had to spend on building that optimizer. That is by no means a good answer or a complete answer to that question, but I at least wanted to address it. Are there any other questions, or else I know everybody's it's Thursday, so everybody has a beer to drink.
So thank you, Keith. It was an excellent presentation on your domain, supply chain. That's definitely unique. So folks, you can unmute yourself if you want to chime in or ask a question. Let's see. There is any.
I see a question about fast AI.
Okay.
I honestly haven't used fast AI for a lot of the products that they offer, so I can't speak to that personally. I can say I'm a huge fan of a lot of the blog posts that the fast AI team put out. They're generally pretty on top of new technologies that are coming out, of really interesting things that data scientists may want to pay attention to. That's not necessarily an endorsement for any of the products or solutions that they have, but I definitely say that when they write a blog post, it is generally very well written and extremely accurate on the topic.
All right, folks, thank you for joining us today. It's Thursday evening and spending some time with us, sharing your thoughts. I hope to see you in our next meetup and join us. We'll be announcing it pretty soon. And I think, Keith, maybe do you want to share the slide sometime? We can post it in meetup if you want, or I'll be sharing the recording on our YouTube channel once we get it together.
Oh God, this was recorded.
Yep. No problem. Is that no? Hopefully that's not an issue. I can.
No, it's not an issue.
Okay. Okay. Sorry. Yeah, I should have mentioned it before.
Excellent.
Okay. Thank you again. See you next time.